In June 1940, war had swept across Europe like a flood of iron. Every dispatch sent to Washington was a crack in the belief that America could stand apart. From Poland to France, every fortification, every defensive doctrine had collapsed under the treads of the Blitzkrieg. It was a moment when industry was no longer a field of production, but the boundary between survival and erasure from the map. Amid those days, in an office in Highland Park, Michigan, a 7-minute phone call reshaped the way America thought about power. William Knudsen, appointed by President Franklin D. Roosevelt as Commissioner of Industrial Production, picked up the phone and went straight to the point. Can Chrysler build tanks? On the other end, K.T. Keller, president of the Chrysler Corporation, did not hesitate. I don't know. I've never seen one of these things. The answer sounded like an admission of failure. But in truth, it marked the beginning of a new logic. If something had never been seen before, it could be learned and built. Those 7 minutes became the mental blueprint for what would later be called industrial courage. According to the U.S. Army Ordnance Review, 1940, at that time, the U.S. Army possessed only 66 medium tanks, many of which were already obsolete from World War I. In the global strength rankings, the United States stood 19th, behind even Portugal. On the European continent, Germany had deployed more than 3,000 panzers, crushing Poland in 26 days and sweeping through France in 6 weeks. Each statistic was a warning. If mechanized warfare was the measure of the future, then America was standing at the edge of the age. Reports coming from Paris deeply worried the U.S. War Department. In an internal memo, General George Marshall wrote, "We are not ready, not even close." At that time, the American Army still relied on horse-based logistics, and its armored units were purely experimental. Rock Island Arsenal, the largest tank manufacturing facility in the country, produced only 3 tanks per month, each taking 12 weeks to assemble by hand. Mechanics had to grind each pin, measure each steel plate, and fit each armor panel by eye and experience. Every tank was different, no two were alike. The method bore the mark of the 19th century, while the world had already entered the century of speed. When Keller took the call, he understood that the issue was not one of manufacturing technique, but of how to think about production itself. The Germans had turned factories into strategic weapons. Meanwhile, American ordnance plants still operated like oversized workshops, dependent on individual craftsmanship. "This isn't industry," Keller told his colleagues after the call. "This is sculpture." That statement marked the beginning of a new understanding. Victory would no longer be measured by the number of weapons in storage, but by the speed with which ideas could be transformed into products. According to the War Department memorandum, July 1940, Keller wired Knudsen just hours later, requesting to see the current tank designs. He wanted to understand the problem not from the structure of the tank, but from the production chain itself. If we can make 3,000 cars a day, we can make tanks if you let us think like car builders. The difference lay in mindset, not in steel. The nation's fear of failure was becoming the private sector's drive for innovation. In Washington, anxiety spread to the political level. Roosevelt demanded that industrial corporations prepare for full mobilization, according to U.S. Senate defense hearings, 1940, projections showed that Germany could reach a production of 1,400 tanks per year, while Britain could produce only about 1,000. The United States, however, had no system capable of mass production. Those numbers turned fear into an equation. The need was not just for tanks, but for a new way of producing them. Knudsen, who came from General Motors, understood the language of the assembly line. He knew America's strength did not reside in its armories, but in the heartbeat of Detroit's industry. Keller understood that too. In a closed meeting with his top engineers, he said, "The Army builds weapons, but we build repetition, and repetition wins wars." The words sounded cold, but they were precise. In a world where bombs fell by the hour, production speed had become the only form of defense. From that point, the notion of a morality of efficiency began to take shape. No one called it that, but everyone felt it. When an engineer shortened a welding step by 10 minutes, he wasn't merely saving time, he was shortening the war. Inside the factory, each worker was a variable in the equation of survival. The line between technique and responsibility no longer existed. On the night of the 10th of June 1940, Keller wrote in his personal notebook, "Fear builds faster than steel." The handwriting shook, the ink blurred, but it remains the only surviving note from that moment of inception. Fear had been transmuted into structure, a form of organizational energy that spread through factory floors, design offices, and technical drawings. The buildings had no roofs yet, but the idea of production as power was already taking form. According to the National Archives' Industrial Mobilization File, just 3 days later, Knudsen's advisory group officially proposed the creation of an entirely new tank factory, something unprecedented in American history. Its name would later be the Detroit Arsenal Tank Plant, designed by architect Albert Kahn. The project was not merely a production plan, it was a declaration of an era to turn fear into an engine. In the War Department conference room that day, light reflected off the burning map of Europe. A young officer wrote in his diary, "They talked about numbers as if they were prayers. The numbers had become a new religion, and efficiency its creed. And in that moment, America stopped fearing defeat and began fearing delay. Fear had been redefined, and from it, a new industrial structure was born." After the June 1940 phone call, K.T. Keller knew he needed a group that could think differently. He summoned 3 names that would later be seen as the nucleus of the Industrial Revolution of War: B. Hutchinson, Owen Skelton, and Frank Zeder. They carried no military rank and were not bound by the regulations of the Ordnance Department. They were mechanical engineers of the automobile age, men who believed that any problem of metal could be solved by logic. In the Highland Park office, they met every night, doors closed, no minutes taken, no military observers present. Internal documents called them the Tank Committee. According to the U.S. Ordnance Mobilization Memo, August 1940, the group's objective was to find a way to produce 1,000 tanks within 18 months, an order the military deemed impossible. Hutchinson, formerly head of engine design, set the first rule: "We don't copy arsenals, we design factories." The statement became the project's motto. From that point on, they did not discuss tanks as a military product, but as a system that could be standardized, subdivided, measured, and replicated. Skelton was the first to raise the issue of method. While the government arsenals depended on individual craftsmanship, he saw the greatest weakness of the old model. Every craftsman builds differently, so every tank is different. Speed could not exist in an environment where error was a habit. Skelton proposed applying automotive tolerances, where every part had to stay within micrometer limits. If car pistons can fit perfectly at 3,000 revolutions per minute, tank parts can fit under fire. The argument convinced everyone. Hutchinson introduced the second idea, the moving assembly line. He described the current process at Rock Island Arsenal as men walking around a stationary tank, wasting energy in circles. Instead of men moving around the object should move past the men. Each worker would perform a fixed operation as the tank slid along a continuous rail. According to the Chrysler Engineering Report, 1940, Hutchinson estimated that by applying this model, assembly time could be reduced from 500 man-hours to about 150, an increase in productivity of over 300%. During the meetings, Frank Zeder was responsible for calculating the inspection process. He understood that speed only had meaning when controlled. "Speed without measurement is chaos," he said. Zeder required every operation to have quantitative parameters. From the torque of a bolt to the flatness of an armor plate, everything had to have a standard value. The engineers established over 1,200 inspection points throughout the line, creating what the military called statistical quality control. According to the Army Technical Bulletin 41, 1941, this was the first time a statistical inspection process had been applied to American weapons manufacturing. The engineering mindset spread quickly. During discussions, Keller spoke little. He only asked one question: can it be repeated? Every proposal had to answer that question. If a method depended on individual talent, it was discarded. If it could be taught to others, it was kept. This principle gradually turned the Tank Committee into a laboratory of industrial philosophy, eliminating randomness, replicating action, redefining the value of skill. According to engineer Charles Fenton in his 1957 memoir, the atmosphere in the meeting room felt like a battle of minds. They were not trying to build tanks, they were trying to build time. Fenton recalled Hutchinson's voice when he said, "Every second we save in Detroit will save lives in Europe." It was no longer a metaphor, but a strategic logic. When war was measured by output, every second on the assembly line equaled every minute on the battlefield. By September 1940, the group had completed the first factory model plan. They called it the Chrysler method. In the report submitted to the Ordnance Department, the model was described as consisting of functional blocks, machining, welding, assembly, testing, and inspection, connected by a straight transfer line nearly 1/4 mile long. The entire layout was based on the principle of linear flow, material moving in one direction, without crossing paths. Keller wrote in a letter to Knudsen, "If we can make material flow without turning back, we can make war shorter." When the military reviewed the proposal, the initial reaction was skepticism. The Army Ordnance Board meeting November 1940 report stated clearly, automotive tolerances are insufficient for combat vehicles. Many officers believed mass production methods would reduce battlefield durability. Keller replied in a meeting, "You want perfect tanks or enough tanks?" The question silenced the room. He understood that speed was not only a matter of engineering, but a moral standpoint, accepting small risks for greater gains. By the end of 1940, the Tank Committee had become the nervous center of the entire project. They began to calculate every minute action, how many steps it took to move between 2 points, how long to change a tool, and how much force was needed for a standard weld. Every detail was quantified, every motion modeled. One engineer joked, they were turning human motion into geometry. Yet behind the joke lay truth. For the first time, human movement was treated as a unit of productivity. According to the Detroit Industrial Archives, File 21, 1941, when the plan was presented in Washington, Keller gave no speech. He simply submitted a chart, one column showing the old process, the other the new. At the bottom, the last line read, "Time saved per unit, 350 hours. No further explanation was needed." From that point, the concept of speed took on a different meaning. It was no longer the result of individual effort, but the product of organization. Speed became the moral measure of the entire system. Those who followed the process were good. Those who slowed it down were obstacles. According to Hutchinson, we were building discipline, not just machines. And in the silence of the meeting room, it sounded like a declaration. When the Detroit Arsenal plant broke ground, the engineers already saw themselves as parts of a greater machine. Each person was no longer just a specialist, but a link in a shared logic, reason, method, speed, discipline. From that moment, American industrial thought entered a new era, and in that silence, the first rhythm of war began to sound not from the battlefield, but from the drawing board. When the Tank Committee proposal was approved at the end of 1940, the next problem was physical: how to turn the theory of speed into real space. Keller understood that if the production process was an idea, then the factory had to be the physical form of that idea. He needed someone who could draw the geometry of efficiency, an architect who understood industry as a living organism. The only name that came to mind was Albert Kahn. At 71, Albert Kahn was already a legend. According to the American Institute of Architects record, 1939, he and his firm, Albert Kahn Associates, were responsible for designing 19% of all architect-engineered industrial buildings in the United States. From Ford's River Rouge plant to metallurgical facilities in Chicago, his works followed one principle: light, air, and the flow of materials must serve productivity. He once said, "A factory must work like a lung, breathing steel in, breathing products out." Now, Keller wanted him to apply that philosophy to war. In July 1940, Khan accepted the task, despite his failing health. He set up a temporary office inside Chrysler's engineering complex in Highland Park and sketched his first concept on a sheet more than 2 meters long. According to the Khan Associates Construction Diary, 1941, he demanded 3 things: no supporting columns in the main shop, maximum natural light, and a one-way material flow. Every detail had to be submitted to the order of production. Khan told Keller, "We are not designing a building, we are designing movement." The official blueprint was submitted on the 2nd of September 1940. The factory, named the Detroit Arsenal Tank Plant, was located in Warren Township, Michigan, covering 113 acres. The main building spanned 1.25 million ft squared, making it one of the largest industrial structures in the world at that time. The walls were 3 feet thick, made of reinforced concrete to withstand near-bomb blasts, and the steel frame roof was designed to disperse shock waves. The main assembly line ran nearly a quarter of a mile, divided into 25 consecutive functional zones, from machining, welding, assembly, and painting to inspection. According to the U.S. War Department Construction Report 1941, construction began on the 9th of September 1940, just 3 months after Khan received the assignment. More than 2,000 workers labored around the clock in 3 shifts. Khan chose precast concrete over traditional steel framing, cutting construction time by half. By February 1941, when the main structure was completed, the walls were still unpainted and the windows not yet installed, but the factory was standing firm. Keller did not wait. He ordered machinery to be moved in while the concrete floor was still drying. Photos in the Detroit Free Press, 1941, show cranes lowering lathes into a building still surrounded by scaffolding. Workers moved through welding smoke and cold air. With the central heating system not yet installed, Keller had a steam locomotive pulled into the center of the plant and opened its valves to warm the first assembly zone. Heat and machinery noise blended into the distinctive sound of a factory not yet finished but already alive. One engineer wrote in his diary, "The factory looked alive before it had a roof." It was the first symbol of the build before it's finished mindset. For Keller, perfection mattered less than progress. He told his management team, "A deadline is not a date, it's a moral limit." The phrase later became a familiar quote across the defense industry. Producing tanks before the factory was fully completed was a risky act, but it embodied the spirit of American industry at the time, building and fighting simultaneously. Albert Kahn oversaw every structural detail. He required the roof to be 60 feet high, with skylights oriented northward to avoid glare, and reinforced the concrete floor with an additional steel layer in the welding section. On his drawings, he marked a detail that would later become the hallmark of the Detroit Arsenal: an assembly conveyor sunk 4 feet below the floor. Tanks moved along the conveyor with their hulls recessed beneath the surface, so that workers could install the drivetrain, tracks, and piping underneath without using pits or lifts. According to the Industrial Engineering Review, 1942, this design saved over 200 labor hours per tank. The material flow was organized along a west-east axis. Raw steel entered from the west, passed through welding, painting, and assembly zones, and exited to the east as a completed tank. The entire layout contained no intersecting or backtracking points. It was the physical embodiment of the linear flow principle proposed by Hutchinson in the previous section. When the first American soldier walked through the plant, he could move straight along the line without turning, witnessing the entire birth of a war machine. According to the U.S. Construction Logistics Report, 1941, the plant consumed more than 200,000 tons of concrete, 5,000 tons of reinforcing steel, and included over 10 miles of internal rail for conveyors. The ventilation system alone had 1,100 intake vents and 800 exhaust fans. Kahn explained in a letter to his son, "The purpose of every beam and window is discipline. Even light must obey order." To him, architecture was not art, it was an instrument of control. By March 1941, When the first M3 tank was completed, part of the south wall was still unpainted, yet the plant was running smoothly. The Detroit Industrial Progress Bulletin, 194, reported, "It is the first building in history designed to move." That statement summarized the philosophy of the entire project. Production was not merely a human activity, but geometry made animate. In that vast space, light from hundreds of windows fell onto the pale concrete floor. The sound of welding hammers echoed under the steel vaults. Young engineer James Lanier recalled in a 1953 interview, "Standing there, you could feel the building breathe. Every column, every line was in rhythm. People began to call the plant a cathedral of production, not because it was beautiful, but because it made one feel small before the power of order." Keller walked along the assembly line on the first trial day. He stopped in the welding section, looked at the haze drifting across the ceiling, and said, "This is what fear built." A short sentence, but enough for those around him to understand that the Detroit Arsenal was not merely a structure, it was the crystallization of a nation's state of mind in crisis. And in that moment, the geometry of production became the geometry of power. Space had become thought, and that thought was forged from steel, light, and discipline. Before moving to the next part, if this story resonates with you, please like and share so more people can see it. Leave a comment with your thoughts. Every word from you will inspire us to create more great videos. When the Detroit Arsenal tank plant began operations in early 1941, the atmosphere on the shop floor felt like an experiment on the limits of man and machine. Every detail on the production line was arranged with absolute precision. The idea of speed, born from Hutchinson and Skelton's blueprints, had now become a production discipline. Here, there was no room for randomness. Every motion had a reason, every sound had meaning. The engineer no longer creates by intuition but obeys through numbers. The first change appeared in the tank hull. Since World War I, traditional tank structures had been assembled using thousands of steel rivets, each one drilled and driven by hand. The process took weeks, required skilled crews, and was prone to error. According to the U.S. Army Ordnance Evaluation 1941, each M2A1 hull required more than 10,000 rivets, and assembly time could exceed 12 days. Keller saw this as proof of an outdated era. He told his engineers, "Rivets belong to the past, welding belongs to the future." Chrysler decided to replace all riveted structures with welding technology. The armor plates were joined by continuous welds, forming a seamless hull instead of a patchwork of plates. This change reduced hull assembly time from weeks to a few days and decreased weight by an average of 200 kilograms per vehicle. According to the ballistic test report, Aberdeen Proving Ground, 1941, Chrysler's welds withstood 1.4 times the pressure of riveted armor during 37mm gunfire tests. The results surprised the Ordnance Department. One officer wrote in the report, "The welds did not fail before the steel did." From then on, welding was no longer just a method but a symbol of mechanical precision. The issue was skill. Previously, welding had been considered a craft for experienced workers, but Keller would not accept that. He demanded a system of jigs, steel frames, fixing each armor plate in place, allowing new workers to weld at the correct angle after only a few hours of training. "We don't teach men to weld, we teach machines to hold," Hutchinson said. According to the Detroit Arsenal Training Bulletin, March 1941, new workers required only 2 weeks of training to meet production standards. Welds were inspected by X-ray to ensure uniformity. When the first beams of light swept across the armor, the image itself became a declaration of a new era. Technology had replaced intuition. Innovation spread to the drivetrain. The original gearbox of the M2A1 was hand-fitted and required expert mechanics to align each gear. The process took about 40 hours. Skelton redesigned it entirely, shifting to a modular structure of pre-assembled blocks that could be fitted on the production line. Time dropped to 4 hours, with precision guaranteed by differential gauges. At the inspection bench, the click of the measuring tool replaced the mechanic's voice. One engineer recalled, You could hear the sound of precision. It was mechanical, not human. The suspension system was also standardized. Each bogie, the most load-bearing structure, was now produced in 2 hours and attached to the hull in 20 minutes. Every bolt position was marked in red paint to help workers orient themselves. According to the Factory Operations Summary, June 1941, Chrysler maintained assembly deviations under 0.01 inch, a figure never before achieved in American ordnance manufacturing. Individual skill gradually disappeared, replaced by the precision of instruments. The jigs and gauges became invisible supervisors, but the greatest challenge lay in the tank's heart, the engine. A shortage of supply from Continental, the manufacturer of the R975 radial 400 horsepower engine, threatened to halt the project. Hutchinson and engineer Harry Wilson found an unconventional solution, combining 5 6-cylinder Chrysler engines into a single unit. They called it the A57 Multibank, a circular structure of 5 I6 blocks, totaling 30 cylinders, 1,253 cubic inches displacement, and 425 horsepower. According to the Chrysler Engineering Division log, July 1941, the entire system operated through a shared transmission shaft connected to a central gearbox. When the prototype started, the room fell silent. The engine roared with chaotic but steady rhythm. One engineer smiled. It sounded like 5 hearts beating in one chest. The Army initially dismissed it as unnatural, calling it a Rube Goldberg contraption. Yet, in testing, the A57 performed more smoothly than expected. It could be assembled from existing components, requiring no special production line. Instead of creating a complex machine, Chrysler had produced a solution simple enough to be replicated immediately. According to the U.S. Army Ordnance Test, October 1941, the Multibank delivered an actual 370 horsepower, while consuming 7% less fuel than the R975 model. The new technology not only transformed design, but also reshaped professional ethics. Engineers who once took pride in craftsmanship now sat before control panels, watching gauges and charts. Each needle movement, each hiss from the lathe told them how to adjust. No one discussed the beauty of the product anymore, only efficiency. "We stopped asking what's perfect," Wilson said. "We asked what's faster." The phrase spread across the plant, becoming its unofficial motto. According to the Industrial Psychology Survey, 1942, the working environment at Detroit Arsenal was described as mechanically disciplined. The steady rhythm of machinery had replaced speech. Every operation moved in fixed cadence, like an industrial symphony. It was called obedience by design. No orders were needed, for the technical structure itself compelled compliance. By the end of 1941, when the line reached full capacity, Keller wrote in a report to Knudsen, "We've built machines that can build themselves." It was not boastful, it was true. The engineer's mindset had transcended invention and entered the realm of ethics. Efficiency had become the goal, and speed the highest virtue. In the welding bay, light flared from the joint between 2 steel plates, reflecting on the face of a young worker bent over his task. He did not know he was helping to forge a historical symbol. He only knew the weld had to be straight, even, and within tolerance. Outside, the chill of Michigan seeped through the unfinished window frames. They worked until the clock struck midnight, listening to the A57 engine's final test echo through the space, vibrating with the sound of steel. And in that thunder, engineering had learned obedience. Obedience was no longer a command, it had become the structure of engineering itself. When the technical foundation of the Detroit Arsenal had been established, what was still missing were the people, the living links within that massive machine. Keller understood that speed could not be sustained if everyone in the plant worked by their own instincts. The system had to know how to learn, and to make that possible, the people inside it had to be trained to learn like machines. According to the U.S. War Production Board Report 1941, a single tank assembly line required more than 400 suppliers across 32 states to function. No American enterprise in history had ever coordinated such a vast network. From the foundries in Pennsylvania that produced gearbox casings, to the plants in Ohio that forged armor plates, to the small workshops in Wisconsin making track pins, every unit had to comply with the same standards. Chrysler not only sent blueprints but also dispatched engineers to supervise processes, provided measurement tools, and advanced funds for new equipment. "We didn't just buy parts," Hutchinson said in a 1946 interview. "We taught people how to make them." The system operated like a living organism with memory. Whenever a supplier encountered an error, the data was sent back to Detroit within 48 hours, and corrective adjustments were issued immediately. According to the Supply Coordination Log 1942, nearly 80% of production errors were resolved within 3 days, thanks to continuous feedback between the satellite workshops and the main assembly line. Managers called it a closed learning loop. The entire nation became an extension of the factory, and Detroit was its central brain. Inside the plant, people themselves were being reprogrammed. By August 1941, the Detroit arsenal employed 5,800 workers, most of them farmers, unskilled laborers, and women entering mechanical work for the first time. None of them had ever seen a tank, yet after just 2 days of training, they began operating on the line. According to the Detroit Arsenal Training Bulletin, 1941, Chrysler's training program broke each operation into small motion sequences called micro-steps. A new worker would learn one action, tightening a bolt, pulling a lever, or welding along a guideline repeated hundreds of times until the motion became instinct. There were no lectures, only practice. A metal board hung in the center of the training room, engraved with the words, "Speed is memory." The slogan captured the plant's philosophy. Speed did not come from command, but from muscle memory. A worker named Robert DeVries wrote in his diary, "On my first day, I was told not to think, just repeat. By the end of the week, my hands knew what my mind didn't." The repetition gradually separated labor from thought, transforming work into synchronized behavior. According to the War Department Labor Division report, 1942, the effectiveness of this method became clear within 6 months. By May 1941, the factory was producing 1 tank every 2 days, a small number, yet a breakthrough compared to Rock Island Arsenal, which had built only 3 tanks per month. By September 1941, production had increased to 4 tanks per day, and as war spread to the Pacific, the demand doubled. By March 1942, the line reached 12 tanks per day, or 360 per month. When America officially entered the war, the pace rose to another level. Every bottleneck was scrutinized, and every lost second became a moral issue. Chrysler established a production expediting department, dozens of engineers monitoring each process, recording time per task, identifying where delays occurred, and where replacements were needed. According to the War Production Audit, December 1942, this system enabled the Detroit Arsenal to reach a record of 896 tanks in 1 month, an average of 29 tanks per day, surpassing the total output of the entire German tank industry during the same period. Inside the plant, time became absolute order. The factory whistle sounded at 7 a.m., long and steady like the heartbeat of industry. Thousands stopped, took their places, and bent over their machines simultaneously. According to the Detroit Labor Chronicle, 1943, some workers called that moment the prayer of production. They did not speak, nor need supervision. Everything unfolded like a pre-written score. The rhythm of welding, drilling, and metal striking metal formed a repeating cadence. Each shift resembled a ritual. Outside, snow covered the factory roofs, but inside, the temperature held steady at 28 degrees Celsius, maintained by steam heat from the central boiler. White fluorescent light from hundreds of lamps reflected off the freshly primed steel hulls. One M3, then M4 tank moved slowly along the 4-feet-deep conveyor, from welding to painting to final assembly. A British observer wrote in his British Lend-Lease assessment, 1942, It feels less like a factory and more like an organism that grows tanks. At such a scale, the smallest deviation could cause chaos. Every worker was issued an error code handbook detailing signal light alerts. Red meant stop, yellow meant wait for confirmation, and green meant proceed. When one stopped, the entire section stopped. According to the Chrysler Production Safety Report, 1,942, this system reduced operational errors by 45% and workplace accidents by 32% compared to other plants. Synchronization had reached a level where one could no longer distinguish between voluntary action and command. Keller often visited the factory at night, walking between rows of machines as the third shift worked. He recalled in a post-war interview, "It was like walking through a city that never slept. Every spark of weld was a heartbeat." At times, he paused before the electronic board showing the day's output, each number flicking upward like a pulse. The system had learned how to self-adjust, self-sustain, and self-accelerate. By 1942, the Detroit Arsenal was no longer merely a factory, it was a collective intelligence. Humans, machines, and processes had merged, feeding back into one another, adapting to change. The system learned from errors, from data, from its own speed. No one could command it alone, and no one could stop it. And in that endless rhythm, the factory no longer built tanks, it built precision, habit, and faith in repetition. The machine had learned the first lesson of industry, survival through learning and repetition. By mid-1942, the thunder of the Detroit Arsenal reached far beyond the limits of a single factory. It became the sound of a new religion, the religion of efficiency. From Washington to New York, newspapers described production lines as cathedrals of machinery. Every statistic was treated as a national prayer. "The war will be won in numbers," declared the War Production Board on the radio. Numbers were no longer data, they were promises. According to the U.S. Ordnance Final War Production Summary, 1,946, from 1,939 to 1,945, the world witnessed a steel race. Germany produced about 24,000 tanks, the Soviet Union 105,000, Britain 28,000, and the United States nearly 90,000. Detroit Arsenal alone contributed 22,234, accounting for 25% of total U.S. tank output. Each vehicle rolling off the line stood as proof that the organization could replace genius and process could replace intuition. On the battlefield, soldiers discovered that efficiency was no abstract concept. It was the difference between survival and disappearance. The M4 Shermans leaving Detroit headed to Europe and North Africa, facing Germany's Tiger I. According to the British War Office Comparative Report, 1,944, the Sherman was inferior in firepower, with a 75mm gun compared to the Tiger's 88mm and armour nearly 40% thinner, but it possessed an advantage the Germans could not match: quantity. When a Tiger was destroyed, Germany needed 3 months to replace it. When a Sherman was lost, America needed only 1 day. Victory became a statistical equation. In that world, individual courage dissolved into the curve of production output. The transformation did not stop at the battlefield. It seeped into the mindset of the entire society. Henry Ford once said, "Repetition is civilization." And now that phrase has become prophecy. Factories from Michigan to California replicated the same model, applying the philosophy of the automobile assembly line to warfare. Ford and Chrysler turned mass production into a democratic ideal. Everyone could contribute through repetition. Speed became morality, productivity became virtue. According to the War Manpower Commission report, 1,943, more than 18 million Americans worked in war production, including 6 million women. On the walls of many factories, the slogan, "More is right," was painted in white beside the national flag. In that era, no one called efficiency a faith, yet everyone lived by it. Each time the line reached a new record, newspapers printed it on the front page as a victory. 896 tanks this month, read the December 1,940, headline of the Detroit News. printed in the same size type as reports of triumphs in Europe. People believed that productive power defined the nation, that America was not shaped by its political philosophy, but by its capacity to multiply achievement. The worship of speed reached even management. In an internal memo of 1943, Keller wrote, "Delay is defeat." Those short words became a mantra among executives. Any interruption, even for a few hours, was seen as a moral fault. Engineers recalled that in winter, when snow covered the internal railways, they shoveled every meter by hand so the conveyors would not stop. No one gave orders, because the system itself had trained them to believe that stopping was betrayal. But every creed has its limits. When efficiency became the only measure, people began to fade from the equation of victory. Post-war reports from the U.S. Army Historical Division 1946 recorded that many engineers, after leaving the plants, spoke of a hollow feeling. They had worked 12 hours a day, 6 days a week, yet no longer knew what they were building beyond the numbers. One worker, anonymous, wrote in a letter to his wife, "We make tanks like we make bread, and sometimes I wonder if that's good." That silence was the other side of the industrial myth. When every value was reduced to productivity, the meaning of victory changed too. In a 1945 speech in Detroit, William Knudsen said, "We have proved that production can save democracy." The line drew applause, but in the back row, an engineer who had worked at the arsenal whispered to his colleague, "And maybe it also changed it." At that moment, America triumphed not only with tanks, but with the belief that speed was virtue and efficiency was truth. In the glow of the factories still burning bright after the war, one thing was clear. When people believed in machines as they believed in themselves, war was not only produced, it was worshipped. And in that faith, steel replaced conviction and rhythm replaced soul. That was when efficiency ceased to be a tool and became the faith of an entire civilization. When the war ended, the Detroit arsenal stood in an unfamiliar silence. The machines that had roared without pause for 3 years suddenly stopped, leaving only the metallic echo within the thick concrete walls. On the main gate, the final production board still hung, 22,234 tanks built, with a total output value exceeding $2 billion from an initial investment of $100 million. From nothing, the factory had reached a production rate of 1 tank every 55 minutes, a record unmatched in the history of modern warfare. But beyond the numbers, the lingering question was not how, but why. According to the U.S. Army Ordnance Final Report, 1946, the Detroit arsenal produced about 25% of all U.S. tanks in World War II, but its true impact went far beyond quantity. It created a new model of relationship between humans and machines, between morality and productivity. In a place where speed had once been measured in seconds, people began to realize the cost of turning efficiency into a moral value. Precision, once a tool, had become an ideal. As the war receded, the system continued to live on. Between 1952, 1954, the Detroit arsenal produced 3,443 M47 Patton tanks, followed by the M60 line in the 1,960 seconds, and by 1979, components for the M1 Abrams, the new main battle tank of the United States. Every generation of tanks inherited the same principles from the Keller and Hutchinson era: standardization, optimization, synchronization. According to the General Dynamics Defense Review, 1983, even when Chrysler sold its defense division to General Dynamics for $336.1 million in 1982, the cognitive structure of the Detroit arsenal remained intact as a genetic code of American industry. Yet in post-war technical conferences, those who had once worked on the project began to speak of a deep contradiction. They were proud of having proven the power of production, but they also realized they had laid the foundation for a new form of morality, one in which human worth was measured by output. Historian Paul Koistinen called it industrial morality, a concept in which speed, calculation, and repetition became national virtues. Production as power had once saved the world from tyranny, but it also turned industry into the core of collective belief. At a Smithsonian Institute symposium in 1975, a documentary on the Detroit Arsenal was screened. In the auditorium, as the sound of engines filled the room, a few elderly former workers bowed their heads. They said that each weld, each spark had once been a symbol of pride, but now, hearing it again, it evoked emptiness. One former engineer spoke slowly. "We thought we were building victory, but we were also building a belief." That sentence captured the entire paradox of the industrial age. Between progress and responsibility lies a thin, bright, but fragile weld. The Detroit Arsenal proved that engineering could become the religion of the 20th century, a place where humanity worshipped what it created. From that factory, the world learned that power did not lie in weapons, but in the ability to replicate ideas at the speed of machines. Yet at the same time, it taught that when speed becomes faith, justice grows indistinct. And in that silence after the last tank rolled out, the factory itself became a mirror. If production is morality, then who defines justice? Detroit did not merely teach humanity how to build tanks, it taught that speed could replace belief. Thank you for following this journey to the end of the Detroit Arsenal, where fear became structure, engineering became faith, and speed was exalted as the morality of an era. The machines that left the line now sleep, but the question of humanity and industrial power still echoes through every page of history. Don't forget to subscribe to the channel to follow more of these battles yet to come.